Hello, welcome to Fundamentals of Acoustics. Today is the third day for this week, and yesterday we had developed the momentum equation. What we plan to do in today's lecture is develop the second important equation which governs wave propagation, and that is the equation for continuity. As we had discussed earlier, the continuity equation essentially represents conservation of mass. So, with that understanding, we will develop the continuity equation for one dimensional propagation of sound waves. So, our aim is to develop the continuity equation So, we will once again draw a fluid element and actually this is a control volume. So, it is a volume into which flow is going in and flow is coming out. So, there is inflow and there is an efflux. Okay. The dimensions of this control volume are delta x, and this cross sectional area is delta A. Now, you should imagine this flow volume as some sort of a made up of some sort of a rubbery thing, okay, some sort of a rubbery thing. So, what happens if the amount of flow which is going in and amount of flow going out is same, then the volume of this rubber volume, this will not, it will remain same. But if there is less inflow and or if there is more inflow and there is more outflow, then mass will accumulate inside this rubbery volume and this rubber will expand because mass is going to accumulate in it. So, that is going to happen. So, this is what we think, this is how we are going to develop the continuity equation. The overall process is, so the other thing I wanted to mention is that this expansion is going to happen only in the x direction, and it is going to happen only in the x direction because we are assuming that the variation in y and z directions are 0. So, it will just become either longer or shorter, but it will not become fat or thin. So, outflow minus inflow. So, this will equal to change in mass side volume, change in mass inside volume. So, outflow is what? So, outflow here the velocities. So, once again, so the coordinates of this point are x, y and z. So, outflow, what is the velocity here? Inflow velocity is u x, which is a function of x and t. Okay. At the outlet, the velocity is u x plus delta x, and time is same at that time itself. So, u x plus delta x comma t. We will also write down the densities, because the density of fluid going in and the fluid going out, they may also be different. So, density is rho t x t, and the density of fluid coming out is rho t x plus delta x comma t, and we will say that the density of fluid inside the volume, see, will change from point to point. it will change from point to point because x is changing. So, it may have some average value, rho av is average density in volume. Okay. So, what is outflow? Outflow is going to be u x plus delta x time t comma t times area times delta t. Okay. So, in 1 second the amount of liquid which is going to flow out is going to be u x plus delta x t. So, this is in cubic meters, but then we are interested in mass. So, we will multiply it by rho t x plus delta x t, and then inflow is u x t delta a delta t rho t x comma t. So, we will develop an expression of outflow minus inflow. So, that is equal to u x plus delta x t rho t x plus delta x t delta A times delta T. So, if outflow and inflow is same, then the total sum of these two will be 0, but it may not be, because it may be that inflow is higher, outflow is less, or whatever. So, that equals change in mass in the volume. So, what is change in mass? It is the volume of this element, and the volume of this element is delta tau and times rho average. Okay. So, remember this delta tau is the change in the volume, change in volume. Okay. So, the volume may go up or go down, and that change corresponds to the change in mass. So, change in volume times average density. So, now what we do is we expand these relations. So, from Taylor series we know that u x plus delta x comma t equals u of x t plus del u over del x plus higher order terms. This is from Taylor series expansion. Similarly, we know that rho t x plus delta x comma t is equal to rho t evaluated at x and t plus partial of rho t times delta x plus higher order terms. So, we plug these in the above equation, and what we get is u x t plus del u over del x del. So, that is my first term. Then I multiply it by rho t minus that is my equation. So, corresponding to rho t, this is the term I am getting. Okay. So, now I multiply these two terms which are underlined in green and red and do all the math. So, what I get is so I made a small error, this should have been delta t. Oh, I think I missed an important term, so I have to write that again. I missed this term. So, I have to write that minus this. So, first thing we note is that this term cancels out this term, and I think I omitted one more term here in the parenthesis. So, pardon me. So, I will write it again. I missed the higher order term. This is delta x square minus u of x t rho t x t change in volume times average density. Yeah, now I think we are right. So, as I mentioned, these two terms cancel out. The other thing we note is if delta x is very small, then this term is negligible compared to these two guys, right. So, I can omit this term also. I can omit this term also. So, essentially what I get is u and I am taking delta x out, change in volume rho average. Okay. Now, we make one more assumption. No, okay. So, we make one more simplification. What we do is we shift this rho av to the left hand side. So, I am going to erase average density from here and I am going to put it in the denominator of these terms. Okay. So, now what do we observe? We observe, so we have already assumed that u is extremely small and so u is extremely small, that is one thing we have observed. The other thing is what is partial of density with respect to x. So, this is equal to partial of initial density plus change in density, right. So, this is equal to this density rho naught is constant. So, this is essentially same as partial of rho with respect to partial of x. So, here I can omit this term t and I can make it partial of rho with respect to partial of x. This is important. Okay. Second thing, rho t at position x t is equal to rho naught plus rho of x t and rho average. So, when I divide this by rho average, what is rho average? It is the value of rho t, the average of different values of rho t along the whole length, along this length. At different cross sections I will have different values of rho t's, but at each cross section rho t will be rho naught plus rho x t, right, and rho naught is extremely large compared to rho x t. So, this ratio I can safely say is equal to 1. Okay. So, I can say this is equal to 1. So, I can rewrite my equation as u x t del rho over del x divided by rho average plus del u over del x times delta x delta A delta T equals change in volume. So, this is my continuity equation. Now, we are going to simplify it further. We have to see, compare these two terms. Okay, we have to compare these two terms. So, so this term is partial of u with respect to x and u is very small. This is also u x t and this is also u is very small. So, u and partial of u with respect to x are somewhat comparable. Okay. Now, let us look at del rho over del x, and this is the change in density, its partial derivative with respect to x, and this I am dividing it by a very large number, rho average. Okay. So, this is very small. So, I am multiplying this number and these two numbers. So, this is small, this is all very small, I am multiplying these two. So, when I multiply these two, the product is significantly small compared to del u over del x. Okay. So, I can say that this is very small compared to del u over del x. So, my continuity equation becomes del x del A times, and I am going to move del t to the right side. This is what I get. Now, in the limit del t going to 0, del tau over del t approaches d tau over dt. Also, del x del A equals V t. So, my continuity equation becomes del u over del x times V t equals d tau over dt. So, that is my continuity equation. So, that concludes our discussion on the continuity equation. Last day or in the previous lecture we had developed the momentum equation. Today we developed the continuity equation. Tomorrow we will develop the next equation which relates to the adiabatic process which is occurring in this gas. So, we will apply the gas law and we will develop that equation as well. So, we will meet tomorrow again and have a great day. Bye.